When you're looking at the correlation between the delta plus, the positive charge density on the hydrogen versus acidity, was it pretty much a good correlation between those, or were there some that didn't quite fit? I'll show you a plot, what it's supposed to look like, but it's not a perfect correlation. It's not a perfect correlation because acid strength depends on other factors as well. And so let's take a look at the factors affecting acid strength. The most important thing is we look at the H, the HX bond. And so it's the H, we call it B. B just stands for a generic base. Because once that proton breaks off, then we're left with a conjugate base. And so HB. And so the first thing about acid strength is it's going to depend on how strong the HB bond is. And so we say bond strength here. The examples we saw were HCl and HI. HI has a much weaker bond, or more acidic. But we do need some polarity. There has to be some polarity, otherwise an something like HC would be acidic, but HC is not acidic. Bases aren't attracted to that. And so we need polarity. And the polarity is what we looked at, yesterday. We're looking at the delta plus on the hydrogen, and that was quantitated using the electrostatic potential. Electrostatic potential is like if you take a probe and you try to measure the voltage at some distance from the nucleus. That's electrostatic potential. Polarity. So these two we already looked at, bond strength and polarity, but what are the other factors that influence the acid strength? Another factor that influences acid strength is the stability of the product. Well, what is the product? The product is the conjugate base. There are two things that will impact the stability of the product here. The first is the, actually, let's just call it charge delocalization. Charge delocalization can be enhanced via the inductive effect, or resonance delocalization. And so let's take a look at these two factors now.
The charge delocalization, is that another factor?
Well, the stability of the product is going to be impacted by charge delocalization. And so let me explain what I mean by that. What do I mean by a stable product? Stable means unreactive. Right? And so basically we look at this in terms of base strength. increasing stability means the base strength weakens, and so weakening base strength, let's just say. And so increase in stability means a decrease in base strength. And so let's take a look at base strength. Just in general. And actually this is good because if we look at acid strength, we should also look at base strength. And so what makes a good strong base? So if we have hydroxide, that would be the Lewis structure. Lewis structure, normally what we do is we write all the formal charges. Non-zero ones we don't show. And then we sum it up and put it out there. But a lot of people say, yeah, this is too much. So we get rid of the brackets. And you should probably put it there for a proper Lewis structure. And so we have hydroxide versus oxide. Hydroxide versus oxide. Which one's a stronger base? Now, is this something you would have to look up on a chart? No, because, you know, chemistry is all electrical interactions. And so if this is going to attack a proton, then which one do you think would be more effective at grabbing that proton and pulling it off the acid? You know, which one do you think is going to be more effective at grabbing this H? You know, obviously the more positive that H is, the better. We need a delta plus on this. Delta plus. So this is just electrical interactions. You know, we think in terms of electrical interactions, we think in terms of charge density. And so which of these two bases would be more effective at pulling off a delta plus hydrogen? Maybe it is oxide. It is oxide because well, it's still got 4 pairs of electrons, just like hydroxide has 4 pairs of electrons. So it's not the pairs of electrons that makes a difference.
Doesn't have any positive pole.
Doesn't have any, it has a pole for positive species. You know, a lot of people say, you know, when I ask which one's a stronger base, a lot of people bring up this argument, oh, this is a lot more electronegative, you know, than that, but they're thinking about it totally wrong. In fact, Petrucci, when he talks about base strength, talks about electronegativity, but you have to be very careful how you use electronegativity. Because bases don't want electron density. You know, bases seek out positive species because they're inherently negative or they have negative charge density. What's more, if you're a positive charge, what would be more attractive, a -1 or a -2? -2, because in fact it'd be twice as attractive according to Coulomb's law. You know? And so the force of attraction is going to be double this. If the force of attraction is double, then obviously this is going to be the stronger base because it has more negative charge density. Both of these are oxygens. This is a -1, this is -2. This is -2 has got more negative charge density. It's going to attack positive species more.
So because it has a greater negative charge.
Greater negative charge density. Charge density is what we're looking at. Negative charge density is what I'm... Okay, while talking about negative charge density, let's compare this. We're looking at Bronsted bases. The reason we're looking at Bronsted bases is because Bronsted bases are a little bit more simpler than Lewis. Lewis bases are a lot more difficult. And so I should say Bronsted here to qualify this, because Lewis is quite a bit more complicated. In Lewis, you have to look at the orbitals that result. Bronsted. All right, well, some people will say oxide and sulfide is the same. They're both -2, but they aren't the same. Which one's a more powerful base, oxide or sulfide? Why sulfide? Its atomic radius is bigger, therefore you have -2 over a bigger volume. Whereas oxygen has a -2 over a smaller volume. So which one has a higher charge density, oxygen or sulfide? Or oxide or sulfide, I should say. And so one way to visualize this is, here we have a 2- charge spread out over here. Sulfide's bigger, there's a 2- charge there. Now, which one is going to be more reactive? In other words, the concentrated charge or the dilute charge. In other words, when I look at this, this is concentrated, this is dilute. What's more? What's more reactive? What's more reactive? If you put 10,000 volts on a plate like this, 10,000 volts on a plate like this, or 10,000 volts at the end of a probe like that. You put 10,000 volts on a large plate, you got a large area there, versus 10,000 volts right at the tip of a metal probe. Do you know which one's going to give you a bigger shock? Probably. Yeah, it's concentrated there. Or about 10,000 volts is 10,000 volts, right? -2 is -2. No difference, is there? No, there is a difference, right? And so you say sulfide because sulfide is more dilute. The more dilute the charge, the more reactive it is? Or does that make sense? No, it doesn't make sense. What makes sense is the more concentrated the charge, the more reactive it is.
I want to take back the other day you said something about like ionic acid, right? It's stronger than, for example, like hydrofluoric or something, but hydrofluoric is more likely to track.
Hydrochloric. Hydrofluoric should be the most reactive of the acids.
But it's not the strongest.
Hydrofluoric's weak. But there's another factor that influences acid strength, which we haven't talked about. Hydrochloric versus hydroiodic. Hydrochloric should be more reactive, but the problem is breaking the bond is a lot harder. Hydroiodic is less reactive, but breaking the bond is easier. You see, we have different things at play that we weigh differently. This is part of what the learning process for this is. We memorize little facts like this, little facts, because sometimes it's hard to predict these types of things. And we memorize these little facts as we go along so that we can make better analyses of things we haven't seen before. And so it's more reactive. Hydrochloric is much more reactive because it's got a higher positive charge density on the hydrogen. When you do this, if we were to correlate it, if we were to make a plot like we did yesterday, it'd be all screwed up. if we were to make a plot of, let's see, what did you put the pKa on the X or the pKa on the Y? You put the pKa on the X? Okay. Let's put the pKa on the X. Well, and then we'll just put the polarity here. You know, the polarity is just going to be the delta plus on the H. And we're going to look at HX. X, in this case, it's not HB because X is usually the general symbol given to what? Given to halogens. And so X would be a halide, you know, like chloride, bromide, iodide. We usually use X for. B we use for everything. It's a base. Well, anyway, if we're looking at the delta plus here, you know, the biggest delta plus will be HF. But the biggest delta plus is HF, but it also has a large pKa. A large pKa means it's not very strong. A small pKa means it's strong. Right? And then we have HCl, the next biggest one, but that's strong. That's a strong acid. So that's down here, right? But then we go to HI. HI is less polar, and yet it's stronger. You know, we'll just go HBr, HI. And so we got some funky thing like this, you know, where this is unusual here. HF is unusual. We got HCl, HBr, HI. Hey, that's backwards. That's backwards from what you guys generated yesterday. Well, it's because you have multiple influences on acid strength, right? And so if you notice, yesterday we were just looking at carboxylic acids. And so what we did was we kept the bond strength the same. Now, if you keep the bond strength essentially the same, then the only thing that we would consider is like polarity. I mean, and then polarity, then we see, okay, if the bond strength is the same, then polarity is going to be the major influence. If the bond strength were the same here, and polarity was the only difference, then it would be like this. You know, where HF was the strongest, and then HCl, HBr, HI, like that. Right. But did you know HF is about 1 million times weaker than HCl in terms of acid strength? 1 million times weaker. And so does that mean HF has 1 million times stronger bond? You know, if HF is 1 million times weaker, it's got to be a lot more stable. 1 million times more stable. That means it has 1 million times stronger bond, right? And so let's say let's say HCl bond strength is about 400 kilojoules per mole. That means HF must have a bond strength of 400 million kilojoules per mole. 400 million kilojoules per mole. Does that sound reasonable? No, that's outrageous. If somebody said that, you know, you would say, no, that's crazy, crazy. Because you think about what are some of the strongest bonds out there? Do you guys recall the strongest bond on that chart? Nitrogen-nitrogen bond, nitrogen-nitrogen triple bond. It's considered almost an inert gas. It's so unreactive. You know, air is 80% nitrogen, and that nitrogen is hard to react unless you have special enzymes, or, you know, legume or something like that, right? But what was the bond strength? Nitrogen-nitrogen. 1,000 kilojoules per mole. It wasn't like 400 million kilojoules per mole. 1,000 kilojoules per mole. Turns out there are stronger bonds than that, because when we look at lattices, you know, like ionic lattices, all ions line up, but we're still only talking about 3,000 at the top end, 3,000 kilojoules per mole. Which we're going to talk about ionic lattices in chapter 12. So even, now if we made a plot of bond strength, versus acidity, then it'd look nice. There's a pretty good correlation between bond strength and acidity, right? And so that means bond strength must dominate. Well, how could we have predicted that? And so these are just observations. We just take observations, facts of nature, and we'll see, what kind of correlations we can generate. That's what we're doing. And hopefully we don't miss something. This often happens. Sometimes people miss something, or there's something else that influences it. But we generate these correlations and we see, okay, if we did bond strength versus polarity, then HF is an outlier. Something wrong with that. And so HF, there must be some other factor involved as well. And there is another factor involved in HF. We'll try to talk about that today. Well, anyway, so which one is more basic? Which one's the most basic, you say? Oxide's the most basic, for sure, because oxide has the greatest concentration of negative charge. We call it localized. Localized means it's stuck on the oxygen, right? Okay, well, how about, which one's the weakest? Hydroxide's the weakest. So it goes hydroxide, sulfide, oxide. Unfortunately, our chart has an error in there. Our chart has sulfide as a weaker base than hydroxide, not a stronger base than hydroxide. But I corrected the chart here. This is from more recent data. Actually, the more recent data is from the 70s or the 80s. This chart was copyrighted in 1998. They never fixed it with the current data. That happens sometimes. And so the what we call the Ka is 10 to the minus 19 here actually is quite a bit stronger than hydroxide, but weaker than oxide. So that's what we got here. And so we're looking at negative charge density. The greater the negative charge density on the base, right? The greater the negative charge density, minus x, it's like negative charge density, the greater the strength of that base, the more reactive that base is. Some things are just, some things we gotta, are tricky, Some things are a little tricky, like amide here. Amide's a strong base. But this is just, coming up with generalizations. You don't have to look at these individually as far as the reactivity goes. And so just in general, this is what happens. And so what would you think about the base strength of something like this? What would you think about the base strength? Well, it's kind of like hydroxide, right? But different. This is going to be, do you know the name of this? This is the name of this ion. This hypochlorite. Well, that's kind of like hydroxide, right? Hydroxide has a -1 on the oxygen, -1 on the oxygen. So hypochlorite should be the same in terms of base strength as hydroxide because they both have the same negative charge density. Is that correct? And so we look over here, and then that's our prediction. We come over here and we look at hypochlorite. I hope hypochlorite's on here. Well, hypochlorite's a decent base, but it's weaker than hydroxide. Why is hypochlorite weaker than hydroxide? Actually hypochlorite would be considered a weak base. Hydroxide would be considered a strong base. And so why is hypochlorite a weak base and hydroxide a strong base? Shouldn't they be the same? Yes or no? No, and this is why we do this whole valence bond analysis. I'm not going to do the whole valence bond analysis right now. We're just going to do a very simple one. A very simple one. Oxygen versus hydrogen, which one is going to win the tug of war for these? Or oxygen's stronger, so it's going to pull more charge density away. That makes oxygen more negative, right? Whereas chlorine versus oxygen is much more closely matched, right? So chlorine's going to pull more of that electron density away from oxygen, although oxygen's more electronegative. But chlorine pulls more of the electron density away, making this oxygen less negative. And so even though both of these have a -1 formal charge, the charge density is different. The charge density on this oxygen is greater than the charge density on this oxygen, making this one more basic, this one less basic. This is called the inductive effect. The inductive effect has this pull of electron density, and so chlorine's more electronegative. It has a greater pull for the electron density, reducing the magnitude of the charge here. Okay, so it's just the concentration of the negative charge there. How about hypoiodide? If we compare hypochlorite with hypoiodide, which one should be a stronger base, which one a weaker base? And so a lot of people will say, oh, it's electronegativity. But you got to be very careful how you explain it, because in this case we're explaining the electronegativity in terms of the basic, this is called the active site or the active atom here, the oxygen. And so if we did iodide here, how is replacing chlorine with iodine going to impact the basicity of this? Should hypoiodide be weaker or hypoiodide be stronger? It's going to be stronger. Hypoiodide should be stronger. Why? Yeah, exactly. It's all about the electron density. This is sp3 sigma bond, and electron density is going to be more polarized. So it's more like this. So we got a greater charge localization on the oxygen. This is charge localization here. This charge localization there's kind of this chain effect, that we see. And so we've seen this in other things as well. But let's take a look at some other examples here. Like this. This is the methoxide ion. Methoxide. Methoxide you probably haven't heard about, but methoxide's a powerful base like hydroxide. This is considered a strong base. And it should be, because carbon and hydrogen have about the same electronegativity. Hydrogen's 2,1, carbon's 2,5, so they're pretty comparable in terms of electronegativity. Therefore, the negative charge density on the oxygen should be comparable. Therefore, these should be about the same strength, correct? about the same strength. In fact, methoxide is a strong base, so that's correct. The strand base, the oxygen is going to put a whole electron density like this. Well, what if I have something like this? Trifluoromethoxide. We call these fluoro groups, fluoro substituent. If I do trifluoromethoxide, what do you think about that now? Well, you go, wait, carbon? It's still a carbon. A carbon's only a 2.5 in terms of electronegativity, right?
But with the oxidation state of the carbon change.
Yeah, the oxidation state of the carbon significantly changes. The oxidation state of this carbon is what? It's 246 minus 2. Oxidation state is minus 2 on this carbon. So that's electron-rich carbon, isn't that? We go over here, and the oxidation state is what? Not 0. I mean, you're thinking in the right terms because it has 0 electrons. If carbon has 0 electrons, it's plus 4. Right. Plus 4. And so what's that going to do to the bond? Well, this one, this is what we call an electron pusher. Did I talk about electron pusher? Electron pusher group is electron rich. It pushes electron density to your functional group. The functional group here is this O minus. And so this electron rich, it's going to push electron density to this, making this one quite basic. And the more electron density that gets pushed on the oxygen, the more basic it becomes, right? Hydrocarbons in general are electron pushing group, electron rich.
Sorry, so you said electron pushers are what?
Electron pushers are we call this a substituent in organic chemistry. And so you attach substituents to different functional groups, and they're going to have an impact on that particular functional group. So the functional group we're looking at is this oxygen minus, right? And so if we have, this is called a methyl group. Methyl groups would be electron rich. Methyl groups electron rich. Like methane, methane's electron rich. And so what that does is it pushes electron density to this oxygen. These are just different ways of thinking about it. Ultimately, you could just do this doing valence bond analysis and then figure it out, how the electron dots are distributed, right? Somewhat. Compared to this. So what we're doing is rather than, because if we're drawing the dots, what meaning does these dots have? How polarized it is. In this case, it's just slightly polarized towards oxygen. It's like slightly polarized. And so what we're doing is we're trying to correlate these numbers, And so eventually what we want to do is this. I want to take all these little observations and come up with some generalizations. And so people take all these observations and come up with the generalizations, and then they call these electron pusher groups, because essentially that's what they do, and so you're looking at, it's not really an electron pusher, right? Or it is, because it's electron rich. And so that's one of the generalizations. These are words that, you can come up with too, that makes it more memorable. So somebody says, well, that's a -2 carbon. Well, what does that mean? -2 carbon. Compared to +4 carbon. These are the terms we use to describe it, because sometimes, like a -2 oxygen, is that an electron pusher? No, a -2 oxygen, that's just happy as is. And so there's a whole bunch of memorization that goes into this in order to really understand chemistry. And so people come up with terms like this to help them, get a better feel for the reactivity of these particular groups of atoms or atoms. Whereas this is called an electron withdrawal. A trifluoromethyl substituent would be sucking electron density to whatever it's attached to, right?
If the electron rich, it pushes electron forward.
Right, right, right. Exactly. Electron rich, it pushes electron poor, it sucks. So if, in this case, okay, this is, let's see what color I have. I have green. Electron density is being pushed here. Electron density, a carbon in the +4 versus an oxygen in the -1. Which one do you think is more electronegative? And the carbon in the +4. And so this is going to suck electron density away from oxygen. So if it sucks electron density away from the oxygen, what does that do to the negative charge density on oxygen? It lessens it, reduces it. And so this one is not very basic at all. A very weak base here compared to this would be a very strong base, right? In relation, relative terms. Okay. This is an inductive effect. But what's more significant is something like this. Let's look at some examples of the resonance delocalization, and then we're going to look at some examples of the combination of the two, resonance delocalization plus the inductive effect. Okay. Methoxide's a strong base, as is ethoxide. Ethoxide's a strong base too. You know, ethoxide looks like this. It's just ethanol. Ethanol is not a very good acid, but if you have a powerful enough base, a powerful enough base can pluck the hydrogen off that oxygen and create ethoxide. And so we have the conjugate relationship. A powerful conjugate base means the conjugate acid must be very weak. The conjugate acid of ethoxide is ethanol, very weak. And so this is a powerful base, ethoxide, but if we look at acetate in a lot of ways looks similar to this. So, this pattern's much better. So it has this methyl group on the end here, except this one's a little different. Here we have a negative charge. Are these about the same in terms of basicity, ethoxide and acetate? No, ethoxide is a powerful base. Acetate is a weak base. Acetic acid is moderate acid. Why is ethoxide a weak base? Well, let's look at the oxidation states. What's the oxidation state of this carbon here? 2, 4, 5. 2, 4, 5 means minus 1. Minus 1. What's the oxidation state of this carbon here? Yeah, this would be 1. And so +3, right? And so maybe it's the inductive effect, right? The inductive effect. What causes, a lot of people say, well, what causes this high oxidation is this oxygen. So this oxygen is pulling electron density away from the carbon. This carbon thus is going to pull electron density away from this, right? The inductive effect. And so normally I would say, oh yeah, the inductive effect, you know, and in chemistry we diagram the inductive effect like this. This oxygen sucks electron density from the carbon, which makes the carbon more electron poor, which in turn is going to suck electron density away from this oxygen. And so this is called the inductive effect here. We could just see it. Or you just use oxidation states. Oxidation states will tell you, this is why I wanted you to correlate. This is why I want you to write all the numbers, so you can see how they're all correlated with one another, right? And the thing is, it's hard to have you memorize this means this or this means that, because you need to see a lot of little correlations and memorize a lot of little facts. But acetate's a much weaker base. The inductive effect is not this. You know, we don't explain it in terms of this. The reason why acetate is a much weaker base than ethoxide is because of resonance delocalization. Here, what we see here is that this is what we call localized. That negative charge is localized on the single oxygen atom. But in acetate, we have resonance delocalization, and that we can draw two resonance forms for this. One, and we have another resonance form. And the true structure would look like the hybrid, right? When you compare the hybrid to what you get from MO theory, the hybrid is the one that most closely matches MO theory. You know? In MO theory, we would have an MO that would span both those oxygens. And so in MO, we get two equivalent bonds, bond order about 1.5. Then we have one lone pair that floats between the two. This is still, this is still a +3 carbon here in terms of oxidation state. And so this is a combination, this inductive effect, this carbon, well, I guess you could say it's pulling electron density away compared to this carbon over here, which is not going to be pulling electron density away. And so this is still a +3 carbon, so there's some induction going on, it's pulling electron density. But if we look at the charge, what is the average charge on each oxygen now? The formal charge? -0.5. That's going to be a significant reduction in charge because we're going from a -1 charge now to a -1/2. We cut that charge density in half, which means it's going to be a lot less reactive. In terms of pure Coulomb's law, it'd be half as reactive, right? And so this is the major factor because the inductive effect is not going to cut the charge in half necessarily, right? And so this is resonance delocalization. And so what people do is they look for patterns, right? And the pattern is this. It's a simple pattern. The pattern is the more resonance forms you can draw, the more stable the ion. And so the more resonance forms you can draw, the more stable. Because, the more resonance forms you draw, the more the charge is delocalized over the structure. The more stable it is, the less reactive of a base it is, the weaker the base, basically. And so, for example, sulfate, you can draw a lot of resonance forms for, versus sulfite, which has fewer resonance forms. So sulfate is a weaker, even though both of them are -2. Sulfate is -2, sulfite is -2. But sulfate, you can delocalize a charge over more of the structure, resulting in a weaker base. In fact, sulfate is quite a bit weaker than sulfite. As you can see here on the chart. Actually, both of them are here. This is sulfite here, moderate base, sulfate, very weak. So this is resonance delocalization. And then we can have a combination of resonance delocalization and inductive effect. So for example, if I compare acetate with trichloroacetate, trichloroacetate looks like this. I'm gonna just draw the hybrid as well. Both of these have a -1/2 formal charge on the oxygen. Both of these have the same oxidation state on the carbon. Carbon's going to be +3. So, are they going to be the same strength? The main factor here is the resonance delocalization. But here we're going to look at a combination of resonance delocalization with, well, we look at the next atom over. If you look at the next atom over, what's the oxidation state of this methyl group here? Two, 4, 6, 7. 2, 4, 6, 7. -3. Ooh, that's pretty electron rich. Those methyls are. Methyls are electron rich, right? We look over here, trichloromethyl is, what's the oxidation state on carbon here? +3. Wow. What does that tell you? See, we do all this stuff, you know, these chlorides, -1, -1, -1, the chlorines on here. The hydrogens are +1, +1, +1. So we do this to get a better idea. You know, we draw out all the oxidations. And the formal charges are, like I said, no difference in the formal charge. They're all 0 here. But the way people do this in terms of the inductive effect, they like to use arrows. And so these chlorines are sucking electron density away from the carbon, which in turn sucks electron density away from this carbon, which sucks electron density away from these oxygens, which lessens the negative charge density. And so the negative charge density should be less than -1/2 here, whereas in acetate it should be at -1/2. Does that make sense? And so which one is going to be a stronger base, acetate or trichloroacetate? Which one's a stronger base? Acetate's a stronger base. It's a stronger base because it's got more negative charge density, whereas trichloroacetate would be a weaker base because the charge is further delocalized, and whereas acetate is more concentrated, more localized. Does that? I'm sure. And so we always consider, you know, the stability of the conjugate base. The stability of the conjugate base will tell us